Hello and Happy New Year. This is Fractal Woman, and today we're going to be talking about the hydrogen spectral lines. Okay, so these are the spectral wavelengths slash frequencies that the hydrogen atom emits when electrons transition from one level to another level. Okay, so the creation of this video was inspired by this paper right here, a frequency-based theory of catalysts. Okay, and so I'm just going to read the first paragraph here to give you an idea of what this paper is about. So chemical reactions are driven by energy. The energy comes in many different forms: chemical, thermal, mechanical, acoustic, and electromagnetic. Various features of each type of energy are thought to contribute in different ways to driving the chemical reactions. Irrespective of the type of energy involved, chemical reactions are undeniably and inextricably intertwined with the transfer and combination of energy. An understanding of energy is therefore vital to an understanding of chemical reactions. Okay, so Nikola Tesla, of course, was promoting this idea, and one of his famous quotes is, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." Okay, so the word frequency here is the key word for this video. So what I'm going to be doing is I'm going to be taking these standard equations, standard constants, and standard equations for the hydrogen spectral line series, and I'm going to be converting them to the frequency domain. Okay, so historically, the spectral series have been reported in terms of wavelength and wave number, and what we're going to be doing is we're going to be looking at them in terms of the frequency domain to see if we can maybe extract more information or gather new insights into this phenomenon. And of course, the purpose of trying to understand these things in terms of the frequency domain is in the hopes of coming up with and or discovering some sort of free electricity, free energy machine. And so Master Ivo gave his holiday wishes, said happy holidays, and will 2025 bring free electricity for all. And this was my Christmas wish as well. It was also my New Year's wish. My New Year's wish was that 2025 would bring free electricity for all. And of course, it's people like Master Ivo and others that actually do experimentations with Tesla's work, trying to reproduce what he's done in the past. And so these are the people that I expect to get closer to coming up with a free electricity device, if such a thing can exist. If such a thing can exist, then I believe that these are the kinds of people that will be bringing this about, and hopefully sooner rather than later. So in terms of understanding the spectral lines that are found, that were discovered when looking at the hydrogen atom, basically these are the frequencies, these are the wavelengths that are emitted, if you want to use that word, that the hydrogen atom creates when the electrons are jumping up and down, the different quantized levels. So this schematic here is a good schematic that shows each of the different levels. Keep in mind that this is just a schematic. This is not what the hydrogen atom sort of physically looks like, but in sort of the Bohr model of the atom, you have different levels. So the N1 level, the N2 level, the N3 level, the N4, N5, and N6, and so on. There are more actual levels, but they usually just show 6 or 7 at any one time in the drawings, in the diagrams, schematics of the hydrogen atom. And so the Lyman series, the first series, is shows all of the spectral lines that are created from the N1, from the first level, from the lowest energy level in the hydrogen atom. So you've got the energy from the first level to the second level, the energy from the first level to the third level, to the fourth level, and fifth level, and sixth level, and so on. So the Lyman series, and let's just have a look at it in a different kind of schematic, okay, shows the energy levels. This is would be the energy emitted from the second level to the, when the electron drops from the second level to the first level, or from the third level to the first level, and so on. Okay, so each series has a starting point, or should I say ending point, at a different level. And so this is the lowest energy level in the hydrogen atom. And then the Balmer series starts from n equals 2. And so if an electron drops from the third level to the second level, this would be the wavelength / frequency of light that it emitted, and from the fourth level to the second level, and so on. And then the Paschen series starts at the third level. So if an electron dropped from the fourth level to the third level, then this would be the energy it would emit, and so on. And with the bracket, it starts at 4, and the Buffon starts at 5. Okay, so you can see clearly this is the pattern that you get when the electrons are moving from one level to another level. So each series is distinct in that it is describing the energy levels from each level to the n level, which here it's n equals 1, here it's n equals 2, here n equals 3, and so on. So hopefully that makes sense. It's not really that hard. This diagram here actually makes it a little easier to understand, because you have something that kind of looks like the Bohr model of the hydrogen atom, and you can see the different levels here. So for the Lyman series, the electrons jump from the various levels to the first level, and then in the Balmer series, it's the second level and the third level. So these are just two schematics showing different ways of looking at the same thing. So in this paper, A Frequency-Based Theory of Catalysts, the author talks about this quite a bit, and he also talks about a phenomenon called heterodyning, which is the addition and subtraction of, it's basically wave interference and how waves interfere. And he is primarily focused on the frequency domain, which is why I like this paper. Okay, so he talks about the heterodyning progression in when frequencies add, they also subtract, and so if you have one frequency resonating with another frequency, you get an additive effect and you get a subtractive effect, so you get two new frequencies when you could do this combination. Okay, and so that's called heterodyning. So heterodyning of frequencies is the natural process that occurs whenever waveform energies combine. It results in patterns of increasing numbers that are mathematically derived. So the number of patterns are multiples of the original frequency. These multiples, of course, are called harmonics. For instance, 800 hertz and 1600 hertz are harmonics of 400 hertz. In musical terms, 800 hertz is 1 octave above 400 hertz, and 1600 hertz is 2 octaves higher. So most of us have intuitive understanding of harmonics through our exposure to music. Few understand the mathematical heterodyne basis for harmonics, which occurs in all waveform energies, and thus in all of nature. So then he goes on to talk about the patterns, the interesting patterns that these heterodyning frequencies take on. So he shows this figure here. So the visual pattern, this is the visual pattern created by the heterodyne series from figure 4. So in figure 4 here, he shows all of the ways that the frequencies heterodyne, and this is a graphical representation of that data. And what he's pointing out here is that there's kind of a self-similarity between these pairs of heterodyning in this graph, and he talks about the fractal paradigm. And so this kind of pattern, you can see this pattern is self-similar to this pattern, is self-similar to this pattern, and so on. And so he says mathematics has a name for this. It's called a fractal. A fractal is defined as a mathematical function which produces a series of self-similar patterns or numbers. Fractal patterns have spurred a great deal of interest because they are found everywhere in nature. Okay, so he's talking about, so they are found in the behavior of organized insects and in the behavior of fluids and fluid dynamics. So the visual patterns produced by fractals are very characteristic. Okay, so he's saying that heterodyning also has the property of self-similarity like a fractal, and this is a good reason, I believe, to have a closer look at this. So then he goes on to say the following: heterodynes are fractals. The conclusion is inescapable. Heterodynes and fractals are both mathematical functions which produce a series of self-similar patterns or numbers. All wave energies combine in heterodyne patterns. Thus, all wave energies actually combine in fractal patterns. Once you understand that the fundamental process of combining energies, it is itself a fractal process, it becomes easier to understand why so many creatures and systems in nature also exhibit fractal patterns. The fractal process and the patterns of nature are built in at a fundamentally basic level. As the scorpion said to the frog, "It's in my nature." So this connection between heterodynes and fractals is a good enough reason for us to talk about what we're going to talk about today, which are the resonant frequencies produced by the electrons transitioning from one level to another level. We want to have a closer look at how these resonant frequencies are produced. And so in this video, what I'm going to do now, historically, these frequencies are not reported in terms of frequency. They're usually reported in terms of wavelength. But as you may well know, that I am more interested in the frequency domain. I would like all of the values in my standard to be written in terms of frequency, and so this is what we're going to do today. We're going to convert the language of this to the from the wavelength domain to the and the wave number to the frequency domain. So the calculation of these values, of these wavelengths and or frequencies, is actually quite simple. It involves a constant and a formula. The constant is referred to as the Rydberg constant, and the formula is referred to as the Rydberg formula. So I just wrote something up here in my meta document, in my unified model of the universe document. This is kind of like a living document where I'm adding sections as I am studying different aspects of physics. So the Rydberg constant is a key value in physics that helps explain the light emitted by atoms, and particularly the hydrogen atom. When an atom absorbs energy, its electrons jump to higher levels. When they fall back to lower levels, they release energy in the form of light. The Rydberg constant helps us understand the specific colors of light, or the spectral lines that we see when these energy transitions occur. Johannes Rydberg, a Swedish scientist, developed a formula that describes the wavelengths of light, the frequencies of light that are emitted by the hydrogen atom. This formula connects the energy levels of an atom to the light we observe, allowing scientists to predict exactly what wavelengths of light will be emitted when an electron moves between different energy levels in the atom. Okay. like that. Okay, so the Rydberg formula has been critical for understanding atomic structure and has applications in field of spectroscopy, where it's used to study the composition of distant stars and gases. So when light from different distant stars and gases arrives at to Earth, we run it through a spectrograph, and the spectrograph separates out the light into different patterns, and we study these patterns to see what wavelengths and or frequencies are being emitted by that star or gas, and we can tell the composition of the star and gas based on those spectral lines. Okay, so by convention, the Rydberg constant is defined in terms of wave number, which is the inverse of wavelength, and it has units cycles per meter. Okay, so technically this is a frequency term, only this is the number of cycles per meter instead of the number of cycles per second. Okay, so this is calibrated to the meter. And thus the output of the Rydberg formula also has units of cycles per meter. Okay, this is referred to as the wave number. The inverse of the wave number is meters per cycle, and this is would be wavelength. So in this section, we'll be converting the Rydberg constant and the Rydberg formula, which are both in the domain of the wave number, from the domain of wavelength and wave number to the frequency domain to be more compatible with the language of the own particle model and the X standard. Okay, so as I just recently said, I am rather fond of the domain, the frequency domain, and I'm writing all of my equations in terms and constants in terms of frequency whenever I am able to do that. Okay, so let's first have a look at the Rydberg constant. Okay, the Rydberg constant and associated units are as follows. Okay, so the Rydberg constant, usually written as R sub infinity, is equal to this value here, 1.09737, etc., times 10 to the 7th cycles per meter. Okay, these are the number of cycles per meter. This is a wave number. The inverse of this number would correspond to a wavelength. Okay, so here is a formula. I think Rydberg himself came up with this value through experimentation, and I think it was Niels Bohr who came up with this formula, connected his work, and came up with this formula to get a more accurate value based on some of the constants of nature. So you can see that the Rydberg constant is equal to 1/2 alpha squared. Okay, so this is alpha as in the fine structure constant squared, times the mass of the electron, times the speed of light, divided by Planck's constant. Okay, so this is how the Rydberg constant is mapped out. So to convert the Rydberg constant to the Rydberg frequency, so to convert to the frequency domain, a new constant, which I'm referring to as the Rydberg frequency, is obtained by multiplying the Rydberg constant by the speed of light. Okay, so when you take the Rydberg constant and multiply it by the speed of light, you get this value here, 3.2898, etc., times 10 to the 15th. Okay, the units of the Rydberg constant are cycles per meter. The units of the speed of light are meters per second. Okay, you can see that the meters cancel and you end up with cycles per second. So now we have a constant of nature, Rydberg constant, the Rydberg frequency in terms of frequency. So it has the units of frequency. Okay, so now we're going to have a closer look at this part in brackets right here. So here we notice that the term in brackets is equal to the energy of the electron. Okay, so we see that we have mc squared. So the mass of the electron times c squared is equal to E, the energy of the electron. Okay, and when you take the energy and you divide it of the electron and divide it by Planck's constant, you end up with the Compton frequency of the electron. Okay, so here we notice that the term in brackets is equal to the energy of the electron divided by Planck's constant, which is equal to the Compton frequency of the electron. F sub E is equal to 1.2355, etc., times 10 to the 20 hertz cycles per second. Okay, so we can rewrite the above equation, this one here, as follows. So now we can say the Rydberg frequency is equal to 1/2 alpha squared times the Compton frequency of the electron. So now we have both the constant, we have the constant now in terms of the Compton frequency of the electron, which I find really interesting. So this Rydberg frequency is a fraction of a fraction of a fraction of the Compton frequency of the electron. Okay, so I think this is really important. I think it's really interesting, but I also think it's really important to see the connection between the Rydberg frequency, which we will be using in a minute to calculate the Rydberg formula in the frequency domain, and how it's related to the Compton frequency of the electron. In the Ohm particle model and in John Macken's model of the electron, the Compton frequency is the number of turns, is the number of times that this wave is turning. Now this wave is propagating. It is not spinning. I don't want to use the word spin because it's not spinning in the traditional sense of like a spinning top, but it is turning. The wave is propagating in a circular fashion. It's a soliton wave that is circulating. And so the Compton frequency is the number of turns per unit time per second that this model is turning. So this is the Compton frequency is the number of turns per second of this particular model. Okay, so now that I showed you how to convert the Rydberg constant from the domain of the wave number to the domain of the frequency, I am going to show you how to convert the Rydberg formula to the frequency domain as well. So in the domain of wavelength, the Rydberg formula is written as follows. 1 over lambda, so 1 over wavelength, is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. And here n1 is the principal quantum number of an energy level, and n2 is the principal quantum number of an energy level for an atomic transition. So technically, let's have a look at this graph here. So let's just say N2 would be the transition from, and then N1 is the transition to. So if something is transitioning from N2 to N1, we would use this formula here. So the N2 would be the second energy level, and N1 would be the first energy level, or N2 would be the third, could also be the third energy level, or let's say the fourth energy level to the first energy level. And so here N2 must be greater than N1 so that this term in here will never become negative. Okay, so this formula actually calculates the inverse of wavelength, obviously, and so to get the actual wavelength we need to invert this value. Okay, so now what we're going to do is we're going to calculate the frequency version. Okay, so actually the frequency version is exactly the same. Let's just put them both there. It looks exactly the same, only I'm replacing the Rydberg constant, which is in the domain of wave number, with the Rydberg frequency, The rest of the formula remains the same, and the output of this formula is a frequency term. Okay, so it's as simple as that. So we need to recalculate, we need to multiply the Rydberg constant by the speed of light to get the constant in terms of frequency. And then when we plug that into this formula, the output of that formula is a frequency term. Okay, so this is how to easily get from the domain of the wave number to the domain of frequency with the Rydberg constant and the Rydberg formula. So now what I want to do is I want to play with this formula a little bit. So what I want to do is I want to take this calculation here that we did here, where we had the Rydberg constant in terms of the Compton frequency of the electron, and I want to plug that in here. So instead of writing the frequency is equal to the Rydberg frequency times this, we have the frequency is equal to 1/2 alpha squared times the Compton frequency of the electron. Okay, then we're going to take this a little bit further. What I want to do is I want to take, so it always bothered me whenever I looked at this formula, the alpha squared kind of always bothered me because I wasn't sure why alpha had to be squared. I can't kind of justify in my mind why alpha needs to be squared. And so when you take this alpha term and put it back into the brackets, then we have something simpler on this side. So we have the frequency is equal to 1/2 of the Compton frequency of the electron times alpha squared over the principal number squared minus alpha squared over the principal number squared. And so it gives me a better idea of why alpha needs to be squared, because the principal, the quantum numbers are also squared. Okay, and so we can kind of write it like this to maybe make that more obvious, where you have alpha over the principal numbers squared minus alpha over the principal numbers squared. Okay, so the output of this equation here is the frequency of the spectral line. Okay, so it is the frequency instead of the wavelength of the spectral line. It produces the frequency of the spectral line. And so that is what the purpose of this exercise was, to convert from the wavelength domain to the frequency domain so that we can look at the frequencies and maybe study this a little more in the future. This is as far as I wanted to get with this video here. So the term on the right gives a plausible explanation for why we need alpha squared, which kind of bothered me a little bit in the past. Okay, and so when you kind of attach the alpha parameter to the principal quantum number, you can kind of potentially see why alpha needs to be squared. Okay, so this is how you convert the Rydberg formula and the Rydberg constant from the domain of wavelength and to the domain of frequency. And now we can have a look at these frequencies and see if we can see any connections when you look at them in terms of frequency. And we can go, start looking for heterodyning. Maybe there's some heterodyning going on in there. And so there's more work to be done. This is kind of as far as I've gotten with this. Now, I did write a computer program to generate all of the series based on this formula, and I plotted them in an Excel spreadsheet. So you can see that the frequencies are kind of leveling out. They are each time you go through that iteration of the formula. Okay, so each time you do this, each time you increase the second principal number, to the next energy level, you get a new frequency, and you can see that this frequency is approaching a certain value. And so if you did this an infinite number of times, you would end up with a very specific value. Okay, and so the Lyman series looks like this. The Balmer series looks very similar. In fact, all of these series Just give this a second to come up. The Passion series looks like this. So they all look very similar. They all start off with sort of a steep curve, and they're all kind of approaching a certain value. Okay, so I think we need to look closer at these frequencies to see if there is in fact any heterodyning going on between these different energy levels. The sort of implication here is that the hydrogen atom, or that, the atom in general, is sort of a resonant cavity. It's an object that is resonating with itself and producing all of these very specific energy levels. And, by understanding the idea of heterodyning and how these resonant frequencies combine, we may be able to discover something new. We may be able to discover a way of looking at this that leads to a free energy machine, free electricity for all, as Master Ivo and I and many others have been seeking. Okay, so I'm going to leave it at that. And again, happy holidays, happy New Year, Merry Christmas. I hope you had a great holiday. And well, I'll be back.